Good morning, everybody. We have to talk about independent and dependent events today because in probability, sometimes the probability of something happening stands alone, and sometimes the probability that something happens depends upon something that had happened before it. So that's a really, really important concept. So this is lesson 5, independent events. Now we have a formula to test for independence. And the formula either works and you're independent, or the formula does not work and you're dependent. So if a question ever asks you, are these two items dependent upon each other, you really can only do independent and see if it's either yes or if it's a no. And there's a couple of ways to find out about independence. But before we do that, I just want to give you some examples to try to make it really clear as to what we mean by independent and dependent. Let's talk about rolling a die. Now, when you roll a die, your sample space can only be 1, 2, 3, 4, 5, or 6. Unless, you roll a different type of die. But you're rolling a regular 6-sided die. That's your sample space. Now, no amount of blowing on it, shaking it up, shaking it down, shaking it behind your back is really going to influence what the number is that you get. It's an inanimate object. It is completely independent. So the probability of rolling a 2 is 1 out of 6. The probability of rolling a 2 again is still 1 out of 6. So the probability of rolling a 2 and a 2, now the comma means and, is now equal to 1 out of 36. See, because when we are talking about and with these types of things, what we do is we multiply the individual probabilities together. So when you're dealing with an and on this type of problem, not, the two-way table, the and, you could see the overlap right away. But here, if you are doing each probability separate and you have an and, a comma means and, this means multiply. Okay, so you got to multiply your probabilities together. So the same would be true if, the standard, you have a bag of marbles. So let's say I have this bag of marbles. There's my version of a bag with the little ties. Okay, in it I have a blue marble, a blue marble, a blue marble, a red marble, a red marble, and a white. So what did I make in here? 6. Let's make it 7. Let's put another blue. So the sample space of my bag is listed out. There are 4 blue, 2 red, 1 white. So 4 blue rather. 4 blue, 2 red, 1 white. 7 marbles. Now, when you're doing a problem like this, you're going to be super careful with what it says. If it says you pick a marble, replace it, then pick again. Well, what's happening is you didn't change your sample space at all. It's independent because marbles, again, just like a die, they don't talk to one another. So if I ask you, what is the probability that you picked a white marble and then a red marble? Now, again, you picked the marble, you replaced it. So the probability of my white is 1 out of 7. I put the marble back in the bag. I have 7 marbles still. So, and then the comma, the and, the probability of picking a red is now 2 out of 7. So the probability that this happens with this particular sample space would have been 2 out of 49. So very small chance that that would have happened. Now, if I'm just going to get rid of my die sample space because I want to keep using this bag of marbles. So if we wanted to make a tree diagram of picking a marble, replacing it, and picking a marble. So if I wanted to make a full sample space of picking 2 marbles with replacement, what I have to do now is consider that each marble is separate. I mean, they are separate pieces. So there's blue 1, there's blue 2, there's blue 3, there's blue 4. Then there's red 1, red 2, and white. And there's only 1 white, so let me just make that neater. So there's my white marble now. There's my 7 marbles listed as a sample space. Now this would be the first pick. But if I replace this marble, I have to have blue 1, blue 2, blue 3, blue 4, red 1, red 2, and white. I have 7 branches coming off each one of these. It's a little hard for me to do because I write too big, so let me move my blue 2 over here. Then that gives me, now here's my problem. Wait, let me slow down. No, I did it right, I'm sorry. So I picked the second blue marble, but now I replaced it in the bag. So now I have blue 1, blue 2, blue 3, blue 4, red 1, red 2, and the white to choose from. So now I'm up to 14 branches. I didn't pick the first blue marble or the second blue marble. I picked the third blue marble, but then I replace it. So now I have blue 1, blue 2, blue 3, blue 4, red 1, red 2, and white. All right, I didn't pick blue 1, I didn't pick blue 2, I didn't pick blue 3, I picked blue 4. That means I have blue 1, blue 2, blue 3, blue 4, red 1, red 2, and the white. Seems a little redundant, but this is what you have to do if you had to make a sample space. Now you have to say to yourself, all right, I didn't pick blue 1, blue 2, blue 3, or blue 4. I picked the first red marble. So if I pick the first red marble and then I replace it, I still have blue 1, blue 2, blue 3, blue 4, red 1, and red 2, and the white in the bag. And then you say, all right, I didn't pick red 1. I picked red 2. So here's red 2. In the bag, after replacement, blue 1, blue 2, blue 3, blue 4, red 1, red 2, white. And then the last option would be, on my first pick, that I picked white. Replace it, blue 1, blue 2, blue 3, blue 4, red 1, red 2, and the white again. So now there's my 49 branches. And you have to really, if you have to put a sample space, you have to literally talk yourself through it like this. It seems crazy, but you have to. And if I now go back to my problem that said, what's the probability of white followed by red? Well, white followed by red only happened here and here. 2 out of 49. So if you multiply your individual probabilities, it's a heck of a lot faster than making a sample space. Trust me on that. But let's do a couple of more with replacement. If I said, what's the probability that I got a blue followed by a blue? Well, that's a much larger probability. That happened 1, 2, 3, 4 times here, 4 times here, 4 times here, and 4 times here. That happened 16 out of the 49 times. So that was a lot. Then I want to know, if I said this, what's the probability that they're both the same? Well, both the same means all the double blues, which was 16, but now I got double reds, which is 17, 18, 19, 20, and then the double white, 21. So you can look from your sample space, or you could do the individual probabilities. Let me just take one more, to have you think through it. This is all with replacement. Now, the other thing is you have to look at the wording. It can say, what's the probability that you picked a red followed by a blue, and it might say in this order. Or it can say, what's the probability you picked a red followed by a blue in any order? These are two different problems, because red followed by a blue means the probability of red and the probability of blue. And the probability of red is 2 out of 7, and the probability of blue is 4 out of 7, and that gives me 8 out of 49. Because that order mattered. But if they say in any order, now you gotta say, well, that means I got the probability of red first, and then the probability of blue, or, which is plus, the probability of blue followed by the probability of red. So now look it's an or statement, and or is addition. And is multiplication of probability, but or is addition. So I already know that this one is 8 out of 49 from above, and multiplication is commutative, so this guy over here is 8 out of 49. So this is now 16 out of 49, red or blue in any order. So you definitely want to be reading this very, very carefully. And these are all independent events. Now, what also can happen with this plain old bag of marbles, I want to change it up a little bit now. And if oh shoot. Well, that's all right. Meant to leave that, but whatever. Let's just take the same old bag of marbles. You're sitting there, you're bored, everything's shut down, you're not allowed out. You say, what happens with this bag of marbles if I pick a marble and do not replace it? Then pick again. Think about that for 1 second. My dog will not stop barking, so let me let her in before the neighbors get mad. All right, So here we are. Sorry about that. The joys of working from home. So here we go. We pick a marble and we do not replace it. That means I change the sample space. If I pick a marble out of a bag with 7 marbles and then I don't replace it, my bag is down to 6 marbles. I changed my sample space. Doing something first depended upon what happened second. I have the dependent item going on. So if I said, what's the probability of picking a blue followed by a blue? Well, this would be the probability of blue, which was 4 out of 7. And then the probability of blue, but I don't have 7 in my bag anymore. I kept the first marble. I now have 3 red out of 6. Blue marble. Because I picked that blue marble. So if I come over here, let's pretend like it's gone now. I picked it. So now there are 3 blue marbles, 2 red, 1 white, 6 marbles left in the bag because I took one out and I didn't replace it. So you want to really read carefully because that now made 12 out of 42. Even my denominator changed because, again, I changed my sample space. Picking the second blue marble was completely dependent on picking the blue to begin with. If I go back to 7 in a bag and I said, what's the probability of picking a red followed by a red? Well, this would now be 2 out of 7 times 1 out of 6. And this would be 2 out of 42. And if I said the probability that they're both different, well, both different means the probability that I picked blue, then red, or I picked blue, then white, or the probability I picked red, then blue, or the probability I picked red, then white, or the probability I picked white, then blue, or the probability I picked white, then red. Because if they're both different and I don't give you any other information, you have to think about all the ways they could be different. That's a lot of probabilities to find, multiply, and then or means add up. In this instance, this is when I would think that the sample space would be better because then I can count my branches. So if I picked a blue, there's 3 blues left. And then there's the 2 red. And then the white. Now this is going to happen 4 times. This is happening for blue 1, blue 2, blue 3, and if I would have picked the 4th blue marble first. So again, this would have been if I picked blue 1 first. Then I had 2, 3, 4. But if I didn't pick blue 1, maybe I picked blue 2. And then I would have had 1, 3, 4. Or I picked the 3rd one first, and I have 1, 2, 4. Or if I pick the 4th one, then I have 1, 2, 3. So you have to really, really use logic. And then you say, well, maybe I didn't pick blue. Maybe I picked the first red marble, but then that gives me 4 blues, a red, and a white. Or I picked the second red marble. So that was red 1, this is red 2, and then I still have 4 blues, a red, and a white. Or I picked the white marble, which gives me 4 blues, and a red, and a red. So there's my 42 branches. Now, if they're both different, then I can go through my branches a whole lot easier. Here's different, blue, red, blue, red, blue, white. There's 3 right now. And then I have blue, red, blue, red, blue, red. Now I'm up to 6. Blue, red, blue, red, blue, white. 9. Blue, red, blue, red, blue, white. 12. Red, blue, red, blue, red, blue, red, blue, red, white. So now I went from 12 to 16. And then this gave me another 4. 1, 2, 3, 4, 5. That gives me another 5. And then down here, this is going to give me all of them, all 6. So if we take a minute and we add up, this was 6, 5, and 5. That's 16. And then this was 1, 2, 3, 4 times 3, 12. 16 and 12. This now would be 28 out of the 42. So yikes, when you have to think about whether things are impacting something else, it can be a lot of work. You have to really put some time and some thought into this. Now, if we do this with formulas, which we can determine with formulas if things are independent or dependent. Something like this you can reason out. I mean, you're alive in the world. You know that if you take something, there's not as many left, and so that would impact each other. So taking a marble and not replacing it would be dependent. You made one item, one probability dependent on the other. Rolling a die twice, they're completely independent because, you know, they can't talk to each other. But if you have a quantity and you remove some items from that quantity, then of course you change your probability, and that's dependent. So you have to use real world knowledge and probability. Like, you can't just be a robot. You have to think through. You can't just say, where's the formula? Let me plug it in. So that's the first thing. But now, if we were going to use a formula for independent, we have this. If you have what we just did, so if you have like these real life events, you're independent if the probability of A and then B comes from the probability of A times the probability of B. If you can say, and, you know, maybe you look at a chart. If the and statement, if that overlap, so remember, this was the overlap on our chart or Venn diagram. So, and if the overlap on the chart or the Venn diagram is the same as individual probabilities multiplied together, you're independent. So this is one formula for independent. Now, if you can't apply this to the real world and you just have to take the data they give you, the other formula for independent is this. The probability of A given B. So here now, this is a conditional probability. If the conditional is equal to the first part, the probability of A standing alone. You're independent of each other, because the condition didn't matter. This probability all by itself doesn't get affected by the conditions around it. That makes you independent. So think about that. That's what independent would mean anywhere. If you are a free thinker and you think for yourself, you get the information yourself of, whatever the situation is, and you run it through your own thought processes and you come up with your own decision, you're an independent thinker. If you have to just take a bullet point from somebody else's point of view and then all of a sudden that's your point of view, you're a dependent thinker. You're a follower. You don't think for yourself. So in the real world, we all understand an independent thinker. Now in mathematics, it's the same thing, because if standing alone, you are the same as a condition put upon you, you're independent. So the conditional probability looks like this. This would be the probability of A and B, the overlap, the overlap divided by the probability of B standing alone. Remember, this was the condition. If this probability is the same as the probability of A, you're independent. So we can write the conditional with the conditional slash, or we can write out exactly what the conditional is. But again, if this guy standing alone is the same as this guy being part of a condition, if they're the same, independent. So this was a pretty long video to just set you up with today's lesson. I am going to attach the video from the author where he walks through all of these problems, just because to write them on my whiteboard would take a tremendous amount of time, and right now the technology for the district has kind of failed. I can't use the screen Castify, so I can't use my smartboard until they fix it. And so just going to work with what I have right now, and hopefully you guys will be able to follow this. All right, good luck. Let me know how things are going.